Welcome to my SAT 2 chemistry class. The topic of this session is atomic structure. After Rutherford established the presence of nucleus in an atom containing protons and neutrons, he said electrons revolve around the nucleus in planetary orbits. Electron being a charged particle, when it revolves around the nucleus, it will continuously lose energy and spiral into the nucleus in a matter of 10 to the power minus 8 seconds. But this is not happening. This difficulty was overcome by Niels Bohr when he presented a model in which he said electrons do revolve around the nucleus in circular orbits, but only certain orbits are permitted. He called these permitted orbits stationary states or energy levels. See, Bohr's orbits are like a set of concentric circles as you see in the diagram, which may not be very good, but it is giving you an idea of the orbits which are like concentric circles. Now Bohr said the criterion for an orbit to be a permitted one is the angular momentum of the electron given by mvr should be an integral multiple of h by 2 pi. M is the mass of the electron, v is the velocity of the electron, and r is the radius of the orbit. So if mvr is an integral multiple of h by 2 pi, only then that orbit is a permitted one, and as long as an electron revolves in that, it neither loses energy nor gains energy. The orbit that is closest to the nucleus will have the value n is equal to 1. The next one will have n is equal to 2 and so on. Now, Bohr said an electron which is in the first orbit, like in the case of the hydrogen atom, can absorb energy and jump to higher orbits. I will show you that diagrammatically. When an electron jumps from the level n is equal to 1 to n is equal to 4, say it absorbs energy equal to E4 minus E1. If E4 is the energy of the electron in the fourth orbit and E1 is the energy of the electron in the first orbit, if it is able to gain energy equal to E4 minus E1, it will be able to jump to the fourth orbit. Now it is said to be in excited state. It won't be stable there, so it will emit the excess energy that is gained and would come back to the original state or ground state in one or several steps. See, it can come from 4 to 3, 3 to 2, and then it can come to first level, or it can come from 4 to 2 and come to level 1 in another jump, or straight away it can come to first level, first orbit from the fourth orbit in a single jump. All this is possible. See, the same thing happens here in the circular orbit also. It can go from the first level to second level. That is what I have shown here. Now, corresponding to each energy that is emitted, when it comes back, it emits that excess energy, isn't it? That E is equal to h nu. Corresponding to the energy that is emitted, a bright line is observed at this frequency, at the corresponding frequency. See, for the energy that is emitted at the corresponding frequency given by this equation, you see a bright line in a dark background. So if it is a dark background like this, you see some bright lines at specific frequencies in what is called a spectroscope. The instrument is called a spectroscope. This is called an emission spectrum. The set of lines that you see as bright lines in a dark background in a spectroscope is called the emission spectrum. Each element has its own emission spectrum. Whatever be the method in which it is prepared, or whatever be the source in which it is from which it is obtained, an element will give the same lines at the same frequencies. So it is almost like the fingerprint of an element. This is what is used for detecting elements even when they are present in very trace amounts in minerals. For Bohr's model, this emission spectrum was a great evidence. he could calculate, he could determine the radii of the different orbits, and also he could determine the energies of the electrons in various orbits. Even though Bohr's model of atom was a milestone development in the structure of atom, and he got Nobel Prize for his model, his model of atom was found to be inadequate due to the development of two concepts subsequently. The two are what you see on the screen. One is Heisenberg's uncertainty principle, and the other is de Broglie's dual nature of electrons. Bohr talked of definite paths of electrons around the nucleus called orbits. To determine the orbit of an electron, you should be able to determine its exact position and exact velocity at any point of time. But Heisenberg said, for a subatomic particle like electron, it is impossible to determine this exact position and exact velocity simultaneously. I will write it for you now. The definition goes like this. It is impossible to determine simultaneously the exact position and exact velocity or momentum of a subatomic particle. Due to this, the term orbit of the Bohr's model was replaced by orbital. So, orbit was replaced by orbital. What is an orbital, or how do we define an orbital? Orbit is an exact path, but orbital is a hazy region around the nucleus where the probability of finding the electrons is maximum. If you call this the nucleus, then this will be the orbital. Orbital is not showing so many electrons, but it is the region where the probability of finding the electrons is maximum. Now this is the one energy shell which is closest to the nucleus. At a definite distance, you have another energy shell. So each shell has a set of orbitals of similar size. So this is one energy shell, this is another one, and you have third one. And each energy shell will contain a set of orbitals of similar size. Then the second one is de Broglie's dual nature of electrons. De Broglie said electrons possess both wave character and particle character. That is, a beam of electrons will behave like a wave propagation similar to light. And he gave a relationship lambda is equal to h by mv, where lambda is the wavelength which is associated with the wave character of electron, and mass and velocity are associated with the particle nature of electron. So this is the relationship we gave connecting both the types of behavior of the electron, and calculations based on this relationship or calculations made using this relationship proved his point. The next step in the development of structure of atom is the quantum mechanical model. Erwin Schrödinger described the motion of electron around the nucleus as a wave equation. The solution of the wave equation gave 4 quantum numbers. It gave 4 quantum numbers, and the 4 quantum numbers together give the complete address of the electron in an atom. Now I'll describe the quantum numbers, the limitations of their values, and the significance. It may not make a lot of sense in the beginning, but be a little patient. Once I finish this, I will relate the quantum numbers to the orbitals, then everything will become very clear. Actually, out of the 4 quantum numbers, 3 of them belong to the orbital in which the electron is present. The 4th one is related to the electron itself, whether it spins in the clockwise direction or anti-clockwise direction. So the first of the 4 is called principal quantum number. It is denoted by the letter N, and it can have values 1, 2, 3, etc. As you can guess, the one closest to the nucleus will have n is equal to 1, the second one will have n is equal to 2, etc. It gives you an idea about the size of the orbital. When you say an orbital has value n is equal to 1, it is smaller compared to the one which has a value 2 for n. So as the value of n increases, the size of the orbital will be larger because it will be farther away from the nucleus. The next one is azimuthal quantum number, or orbital angular momentum quantum number. It is azimuthal or angular momentum quantum number. It is denoted by the letter L. And L can have values 0, 1, 2, 3, etc. up to n minus 1. N cannot have a value of 0, it starts only from 1, but L will have values 0, 1, 2, 3 up to n minus 1. The value of L gives you an idea about the shape of the orbital. When L is equal to 0, the orbital is said to be spherical. And when L is equal to 1, it is dumbbell shaped. Dumbbell shaped. And when L is equal to 2 or 3, the shape of the orbital becomes more complex. So anyway, the value of L will give you an idea about the shape of the orbital. The third one is magnetic quantum number. It is given by m suffix L. The value of magnetic quantum number or ml depends on L. That is, for L is equal to 0, it can have values, I will put it this way, ml can have values minus L through 0 to plus L. This is the general rule. Now when L is equal to 0, ml can have value only 0 because minus L through 0 to plus L, so this is 0, so you can have only one possibility, that is 0. ml is 0. When L is equal to 1, ml will have values of minus 1, 0 and plus 1. When L is equal to 2, ml will have values minus 2, minus 1, 0, plus 1, plus 2. So it gets 5 values for one value of L, that is L is equal to 2, and so on. For L is equal to 3, ml will have values minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Now I can tell you that ml value gives you the number of orbitals in a subshell. You have a shell, say, which is given by the value of n, and you have a subshell which is given by the value of L, and ml gives you the number of orbitals in each subshell. The last one is spin quantum number, which can have values, only two values, that is ms. It can have only two values, that is plus half or minus half, depending on whether this electron is spinning in the clockwise or anti-clockwise direction. As I told you earlier, the first three quantum numbers, principal, azimuthal and magnetic, belong to the orbital. Spin quantum number belongs to the electron, but all the four numbers together give the complete address of the electron, I said. That is, the electron assumes the first three quantum numbers from the orbital and the fourth quantum number depending on its spin. Now I will relate the quantum numbers with the orbitals. The first shell is K shell. It will have n value of 1 and L value for that will be 0, because I told you L can have values only up to n minus 1. So there is only one value possible, that is L will have a value of 0. Then ml naturally it becomes 0. And this orbital is called the 1s orbital. This is the name of the orbital. Name of orbital. This is 1s orbital. So this is 1s orbital which is spherical in the first shell, K shell. Now L shell. Let us take the second one, which is called L shell. It will have a value of 2 for n. So what are the possibilities for L? It can have values 0 and 1. And for this value of 0 for L, you will have an ML value of 0. And for this value, you will have minus 1, 0 and plus 1. Isn't it? So this set of quantum numbers give you tell you that the orbital is 2s orbital, because L is 0, it is spherical. This is the 2s orbital. 2 because it is in the second shell. That 2 comes from the n value. Now this will belong to the next another orbital that is in the second shell, that is 2, 1, minus 1. This is called before that I'll tell you, when L is equal to 1, I said it is called p orbital, isn't it? So the three orbitals together are 2p orbitals. We can call them now 2px, 2py and 2pz. So I mean this. See 2, 1, 0, 2, 1 plus 1, 2, 1 minus 1. 3 orbitals, 3 sets of orbitals. The next one is KL M shell. Now you will be able to write it yourself, I think. L will have value of 3. So for 3, what are the L values possible? N value 3, what are the L values possible? 0, 1 and 2. So ML will be 0 for this. This will indicate the 3s orbital, spherical orbital. For 3, 1, you will have values minus 1, 0, plus 1. The set of p orbitals, 3p orbitals called 3px, 3py and 3pz. And for L is equal to 2, you will have minus 2, minus 1, 0, plus 1, plus 2. These 5 orbitals together are called 3D orbitals. 3D orbitals, these are called 3D1, 3D2, 3D3, 3D4 and 3D5. And so on. You can go to the next one, N shell. For 4, it will be 0, 1, 2 and 3. I'll show them. For N shell, N value is 4, L value 0, 1, 2, 3, ML value will be 0, minus 1, 0, plus 1, and here it will be minus 2, minus 1, 0, plus 1, plus 2, and this will be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. You find that you have 7 orbitals here. This will be the 4s orbital, 4s spherical orbital, and these 3 together will be the 4p orbital double shaped ones, and these are the 5 numbers of 4d orbitals, and these are the 7 numbers of 4f orbitals. So when I tell you the orbital in which an electron is present, you will be able to give all the 4 quantum numbers of the electron. I will teach you how to find it. Here the n value tells you the number of the shell, distance of the shell from the nucleus, or the size of the shell. L value tells you about the subshell. When L is equal to 0, it is the S subshell. When L is equal to 1, it is the P subshell. When L is equal to 2, it is D subshell. And when L is equal to 3, it is F subshell. ML value tells you the number of orbitals in a subshell. When ML value is 0, that is only one orbital. That is why the first shell has only one orbital. When L value is 1, since 3 values are possible for ML, there are 3 orbitals in the P subshell. L is equal to 1 is P subshell and there are 3 orbitals in P subshell. Totally there are 1 plus 3, there are 4 orbitals in the second shell. 1 s orbital and 3 numbers of P orbitals. Then when L is equal to 2, ML has 5 values. That means there are 5 orbitals in the D subshell. 5 orbitals in the D subshell. So we understand that the third shell has 1 number of S subshell, 3 numbers of P subshell and 5 numbers of D subshell. Altogether there are 1 number of S orbital, 3 numbers of P orbitals and 5 numbers of D orbitals. There are altogether 9 orbitals in the third shell. When L is equal to 3, there are 7 orbitals present in the F subshell. L is equal to 3, it refers to the F subshell and there are 7 orbitals present in the F subshell. So in the fourth shell you have 1 S orbital, 1 number of S orbital, 3 numbers of P orbitals, 5 numbers of D orbitals and 7 numbers of F orbitals. Altogether there are 16 orbitals present. The 1s orbital can be designated as 1, 0, 0. 2s orbital can be designated as 2, 0, 0 and 2p can be designated as 2, 1, minus 1, 2, 1, 0 and 2, 1, plus 1. The 3 orbitals are along the 3 axes and they are equivalent. And you can write for these two, I will show for the D subshell now. You can write the quantum numbers of the D subshell as D, 3, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, plus 1, 3, 2, plus 2. So this is how the orbitals are designated. So when you are given the quantum numbers, you can easily find out which orbital it refers to. Now when an electron is present in this orbital, say 1s orbital, it will have an additional quantum number due to its spin. So the electron will have 4 quantum numbers. Let us write the quantum numbers of one electron that is present in the 1s shell. It will have 1, 0, 0 plus half and the other one will have 1, 0, 0, minus half. There is one more rule here, that is the 2 electrons that are present in an orbital should have opposite spins. Since there are only 2 values possible for the spin, it limits the number of electrons present in an orbital to 2. I suppose you understand. There are only 2 values 2 values are possible for the spin quantum number, and the 2 electrons that are present in an orbital should have opposite spins. So you cannot fit a third electron which will have a same spin as this one or this other one. So we cannot accommodate a third electron in this orbital. So the number of electrons that can be accommodated in the first shell is only 2. If you apply the same rule, the second shell can accommodate only 8 electrons because there are 4 orbitals. So you will have 4 into 2, 8 electrons only can be accommodated in the second shell. Third shell can accommodate 9 into 2, 18 electrons, and the fourth shell can accommodate 16 into 2, 32 electrons. I told you the 4 quantum numbers give the complete address of the electron in an atom. Supposing I write 3, 1, 0, plus half are the quantum numbers of an electron. Can you say in which orbital it is present? Let us try. This is plus half. So, since n is equal to 3, it is the third shell, and L is equal to 1. L is equal to 0 is S, L is equal to 1 is P. So, it is 3P, and 0 is the value of ML. So, it can be either PX, PY or PZ. It can be any one of the 3. They are equivalent. So, you can say this electron is present in the 3P orbital. 3P orbital. Similarly, if I ask you the 4 quantum numbers, if I ask you to give the 4 quantum numbers of an electron present in 4 s orbital, how will you write? Since it is 4s, the principal quantum number is 4. And then s orbital will have L value 0. And when L value is 0, ML value will have to be 0. So it can be 400 plus half, or it can have 400 minus half value. Is that clear? Let's do one more. Let us try to write the quantum numbers of an electron in 3D orbital. 3D orbital. So it will be 3 for the principal quantum number. D will have L value as 2. 0 S for 1, 0 for S, 1 for P, 2 for D. So it is 3, 2. And then the other one can be any one of the 5 permitted values. You can write minus 2, minus 1, 0, plus 1, R plus 2, because it is just mentioned 3D. So let me write minus 2, and the spin quantum number can be plus half or minus half. This will be okay if you write any one of the 2. So this is how we relate the quantum numbers and the orbital, and the quantum numbers and the electrons. To sum up what you learnt about atomic structure, first comes the Bohr's model, which talks of fixed orbits for the electrons around the nucleus. He gave the evidence of the emission spectrum of the element as support for his model. Then came Heisenberg's uncertainty principle and de Broglie's dual behavior of electrons. Because of these developments, the definite path or orbit of an electron, as in Bohr's model, was replaced by orbital, which talks of not a definite path but a hazy region around the nucleus where the probability of finding the electrons is maximum. Then comes the quantum mechanical model, which describes the motion of an electron in an atom as a wave equation, and the solution of the wave equation gives, it's a purely mathematical one, the solution of the wave equation gives 4 quantum numbers, and with the help of the quantum numbers we know how many orbitals can be accommodated in each shell and how many electrons can be present in each shell of the atom. After listening to the discussion, you can take a short test now. There are 10 questions under type 1 and 2 questions under type 2, the true or false type of question. The third type are the multiple choice questions. There may be 1 or more correct options. After finishing the test, you can check with the solution. The explanations for the answers you can find in the discussion.